So please.
Thanks for the introduction. I'd like to start thanking Roland and all the organizers for this nice symposium and for the invitation, of course. So I'll be talking about data-driven transition metal chemistry with evolutionary and deep learning approaches. And so I'd like to start introducing the group and giving the acknowledgements. So we are the UIO Computational Catalysis Group, and we work on different topics, including mechanistic studies and microkinetic modeling. We also do simulation of spectra with relativistic effects and dynamics, and we're also doing work in machine learning. And our common interest is on catalysis and transition metal chemistry. So we are at the Department of Chemistry of the University of Oslo, and we're also part of the Hylleraas Center of Excellence for Quantum Molecular Sciences in Oslo, which also has a node in Tromsø. So here is a recent picture of the group, and so about half of the group now is doing projects in the topic of machine learning for transition metal chemistry and catalysis. And here I have highlighted in red the people that did some of the work that you will see in my slides today. So that is Magnus, Aron, Ainara, Hannes, Trond, and Alejandra. And all of this is supported by external funding from either the EU or the Research Council of Norway. Okay, so why this interest on machine learning for transition metal chemistry? Well, that basically originated from our previous work on a computational catalysis, mostly homogeneous catalysis, and it's actually quite amazing what you can do now with the state-of-the-art DFT methods, so that you can, for example, take a catalyst like this, it's for a cross-coupling based on palladium, and so using DFT model, for example, DFT modeling, you can identify different parts of the catalyst that are relevant to a given chemical process because of different reasons. So for example, in this NHC ligand, we identified relevant electronic effects that were impacting in-cycle chemistry, so chemistry that happens within the main catalytic cycle, which mainly have an impact on the activity of the catalytic system. And then in this R3 and R4 substituents in this allyl ligand, we identified steric effects that had an impact on off-cycle chemistry. So reactions that happen outside the main catalytic cycle, which in this case have an impact on the robustness of the catalyst. So using an steric electronic model like this, together with experimentalists, we could develop novel catalysts with improved activity and robustness. But the problem with these models is that very often they define combinatorial explosions that can yield from a few hundred to a few million catalyst candidates. So the main interest here then on machine learning is how to explore these large chemical spaces. And for this, we've been working on this field for about 5 years now, and we've done a lot of work on predictive machine learning, basically using deep graph learning. But this is, again, predictive machine learning. And what we've been doing more recently is to do generative AI, or generative machine learning. So the main advantage of this is that you don't need to formulate your chemical spaces in an explicit manner. It's rather implicit to it. So when you do predictive machine learning, you use these cheap cheminformatics descriptors from which you do your predictions, but still you need to compute them. If you want to explore millions or perhaps billions of possible chemical species of interest, then even if that cheminformatics representation is very cheap, still it quickly becomes impossible, very impractical to even compute these very cheap cheminformatics descriptors. So with generative AI, you don't have this problem. The underlying chemical space is implicit to your approach. So what I mean with this, perhaps to illustrate this a bit more and have more precise or quantitative view on the nature and the size of these chemical spaces. So you can, for example, think of a square planar transition metal complexes. Here are a couple of famous examples, the cis-platin metallodrug and the Wilkinson's catalyst for hydrogenation reactions. So you can think of generalizing this with this formula, and then you can define a few constraints, like for example, having monodentate ligands. So this would be organic molecules that bind to the metal center through a single atom. And you can define more constraints, like for example, fixing the oxidation state of the metal center to say 2, and also constraining the charge of the ligands and the whole metal complex. So with these constraints, and also taking into account the symmetries of the square planet geometry, you can derive this expression, which gives you the number of unique metal complexes depending on the number of anionic and neutral ligands that you install around it. Now you can plot this, and what you can see is that by using only a pool of 50 different ligands, you can already make more than 1 million different metal complexes. If you extend this pool further to 252 ligands, that you are over 1 billion different transition metal complexes. So these spaces grow very quickly and become vast. Then the other problem that you normally face when you want to apply generative AI to chemical problems is that you very often have to face multi-objective optimization problems. So if you think of catalysis, for example, of course you have to optimize, normally maximize activity, but you also have to take care of robustness or selectivity. If you think of metabolic drugs, or more in general drug discovery, normally at the minimum you're after something that is very interacting with, say, with an enzymatic pocket, and it's also stable. And you can relate this to, for example, polarizability and HOMO-LUMO gap. Of course, drug discovery is way more complicated than just maximizing HOMO-LUMO gap and polarizability, but still, this is sort of a fun benchmark toy task that has been used in all the fields, in quantum-based machine learning in general. And what's interesting about these two properties, and it happens with many other properties, is that eventually if you really want to maximize polarizability, you have to minimize your HOMO-LUMO gap and the other way around, so that these two properties form a Pareto front. So what we did here is to develop a genetic algorithm, because it's been shown that these algorithms are a very strong baseline in generative AI tasks that addresses these challenges. This is this PL-MOGA algorithm, this Pareto Lighthouse multi-objective genetic algorithm, that what it does is to find solutions in selected regions of the Pareto front, so that you can go to the extremes or the middle. You have very fine control over the aim and the scope of the multi-objective optimization that you want to do. But before doing any of this, of course, you have to define some genetic operations to operate in this space. So you can think of these square planet complexes as this chromosome, where each of these dots is a ligand. And then you can define single ligand mutation operations like this. You can also do two ligand mutations where you swap ligands, either in cis or trans, or crossover operations like this one, in which two metal complexes exchange ligands in between them. All of these are full ligand operations that look like this, for example. Then, of course, in order to implement this, you need a ligand library. And so that's what we did next. So we took the Cambridge structural database. We applied some filters to extract crystal structures of metal complexes. We did some DFT and natural bond orbital calculations on this to derive graphs. And this gave us this TMQMG dataset, which is a graph dataset. It contains 74,000 different metal complexes, graph representations of them. So here what we have are the graphs of these metal complexes. We also have Lewis structures from the NBO calculations, and we have the DFT geometries of these metal complexes. Now from here, by simply removing the metal center, we obtain these subgraphs, and now each subgraph is a ligand. We can also infer the ligand charges, and we also have the ligand geometries as they are within the optimized metal complexes. Then you can put all of this data together with some cheminformatics descriptors, like, for example, descriptors that measure steric bulk. And we put all of this together in what we call TMQMGL, which is a ligand library. Now, this ligand library is synthesizable, of course. It all comes from the Cambridge structural database. So these ligands have been made at least once, and there is a reference for it. So they do exist, and in principle can be made again. It's also quite diverse. So here you see some 15 random examples that include 10 different ligand types. So if you take some time to look at this, you will see phosphines, allyls, aryls, carbenes, etc. It's also quite large. So it contains 30,000 different metal ligands. And we also think it's quite robustly defined. So we did some random samples of 500 ligands, and we got like humans, chemists, to actually check things. And we found that spin and charge were consistent for 100% of them. Metal anchors were also valid in all cases. The orders for the denticity and apticity were correct in 97% of them, and the charge was correct for 95% of this. So we think that this is quite well robustly defined. Okay, so once we had this, we started playing around with our genetic algorithm. So we start with this benchmark task in which, so back to this plot here, we took 50 different ligands from this TMQ-MGL ligand library, and we did the full combinatorial explosion. And so in total, you have 1.37 million different metal complexes out from this combinatorial explosion. So here in this scatter plot, you're seeing 1.37 million data points. And for all of them, we computed the so-called ground truth, so polarizability and homolumo gap. You can define a Pareto front here. And so here's what our algorithm did, this genetic algorithm for multi-objective optimization. So starting from this initial random population in blue, over generations 10, 30, 50, and 100, you can see how we consistently approach the Pareto front. So in the last elite generation, we have 130 Pareto front solutions. These include 18 of the 30 non-dominated points that define the Pareto front, and we achieve this after exploring only 1% of the total space. So these algorithms are very efficient. Now, another feature that we have with this algorithm is that we have very fine control over the aim and the scope of the optimization at the Pareto front. So that means that in a way that I will explain now how we do this, we can either, so starting again from this common initial random population in green, we can, and then those at the Pareto front, that's the last generation that we obtained. So you can see that we can aim either at the polarizability extreme or the homolumo extreme or at the middle. And once we decide the aim, we also have control on the scope. So that if we set the aim at the middle, then we can make this like a very narrow oriented optimization, or we can open it gradually. How we do this? Well, at the core of the algorithm, there is this loop here. So basically for any population evolved, we loop over the different targets. So here we have two targets, the homolumo gap and polarizability. We can have three. We're also exploring many objective optimization now. And for each of these populations, we get the median of this target, and then we compare the fitness. The fitness is just the value of that target. You don't need to compose a function that relates the different targets. And then you compare it to the scaled median. And then, depending on whether it's a smaller or larger, you either apply the death penalty to that individual, or you let it survive and be considered as a pattern for the next generation. And this works without, so compared to, say, a weighted sum approach, for example, this works without you needing to know like what are the limits or the relative magnitudes of the different targets you are optimizing. And the other nice thing is that this works with a scaling factor between 0 and 1, depending on how much focus or strength you want to put on the optimization of a given target. Right, another nice thing about these genetic algorithms is that they're very easy to interpret from a, say, chemical perspective. You can, for example, look at how frequently used are the different ligands in your pool as you evolve your elite generation. So this is for the 50 ligands in the pool, and here I'm just highlighting the 10 ligands that are most frequently used to evolve the final elite population. And so then here you can see how the algorithm introduces aryl rings to maximize polarizability, or strong field ligands to maximize the homolumo gap, or both to maximize both targets. Right, then the other thing we did said, okay, let's try to go really large. So we took now a pool of 252 ligands that define a space of over 1 billion different metal complexes. And we run the algorithm. And of course, now we cannot have the ground truth, really, because we could not compute these two properties for 1 billion metal complexes. So what we did here, so this sort of ground truth here, is a sampling of 86,000 metal complexes that we have on another data set in the group. That involves all 30 transition metals and 30,000 different ligands. And these are the values that you get for these two properties. So this is basically a sampling of the Cambridge structural database, what is known today for metal complexes. And what you can see is that when we run the algorithm over this 1 billion space, we really push the results towards the Pareto front. We can do this over the entire Pareto front, or we can also direct it. So here in this example, we've set the focus at the middle of the Pareto front. And the thing is that you push this Pareto front by using only one transition metal, that was palladium-2 here, and 252 ligands instead of the 30 transition metals and 30,000 ligands. And this is what you may wonder, like actually what we get out from this algorithm. Well, we get, metal complexes. Here are two examples from the Pareto front. Here is one is from the 1.37 million benchmark space. This one is from the expression of the 1 billion space. This is maximizing polarizability and gap. Here the size of the ligands was limited to 50 atoms. Here there was no limit, so that when you go to polarizability extreme, you start evolving the sort of monster complexes. For the sake of the proof of concept, we did this with XTB, but we also verified results with the DFT method, like these geometries are DFT verified, and we also verified progress towards the Pareto front. So we get these diverse metal complexes with ligands that can be made, or at least have been made, and we have 3D structures available for them. So we published this recently. There's both preprint and a peer-reviewed article, and also both the data and the code are documented and openly available from GitHub and Zenodo. So then more recently, we have moved our focus from whole complex optimization or generation to doing the same for the metal ligands alone, like isolated. And for this, we've been working now with deep generative AI, and more precisely with a model. I'll try to explain a bit what is this, that it's known as a variational autoencoder. Now these models normally, or these methods normally work with the string representations. So the first thing that we did was to develop a string representation based on smiles that would work for these metal ligands, which is a bit of pain in the neck. But I think we succeeded. So basically, we use this dative bond to lithium encoding for any ligand that has an heteroatom with lone pairs that would coordinate to the metal center. Then for more, say, special bonds, like say carbines, we use different encodings like this double bond to beryllium, and then we use these iridium metallocycles to encode polyidentic ligands. So I'm not sure this is very nice or elegant because it eventually gets a bit weird, but it works. Using this string representation, we can encode any neutral ligand that is monodentate or polydentate, and we can also encode haptic ligands. So ligands in which the atoms that are binding to the metal are neighbors. Charges is a different story. We're still thinking about this and working on it, but we can do neutral, any sort of neutral ligand for the moment. So then next is to do this variational autoencoder. So we use this so-called junction-tree variational autoencoder model. So how does this work? The idea is that your string representation becomes a graph, and then the graph is transformed into a junction tree, which is sort of a coarse-grained representation of a graph, in which you use this ring, bond, and atom clusters. The reason for doing this is that you get higher chemical validity. Actually, you'll see that you get very high chemical validity with this model, so that there are no strange things like, I don't know, hexavalent carbons or things like that, so that the model respects valence rules. So once you do this, so basically you use a graph neural network as an encoder, you learn a latent space representation as a probability distribution, and then there is another neural network that acts as a decoder so that you reconstruct the original input. Now the way in which you train this is by minimizing a loss that has two terms. One is a reconstruction term, so that makes sure that the output of the model is as similar as possible as the input that you are giving to train the model. And there's also a regularization factor that takes care that this is normally mathematically well-behaved distribution, the latent space. So once this is optimized, then what you can do is you can randomly sample this latent space, and then you only use the decoder part of the model to actually generate ligands. This is known as unconditional ligand generation, and here are some examples of ligands that we have generated with this model. So these are monodentate ligands, these are bidentate ligands, and as you can see, the model performs very well, gets very, in the sense of chemical validity, getting very close to 100%. So that means that any of these molecules can be encoded as a mole object in, say, RD kit. Valence rules are respected. There's actually pretty good at the level of novelty, close to 100% novelty, meaning that the ligands you generated are different from the ligands that you use to train the model. Then it's a bit more limited on uniqueness. So there's some redundancy in the output, some repeated ligands. Still, you can reach augmentation for a factor of 7 and 6 for monodentate and bidentate. That means that, for example, with the monodentate model, we can take 10,000 ligands for training, and then you can generate 70,000 ligands that are valid, novel, and unique. Another sort of funny thing we can do with these models is you can add an additional auxiliary task in which you use a predictor to map this latent space into some chemical property of interest. What we did here to push a bit what has been done before for organic molecules is to do this mapping not to one property but to two properties. And then we tried to do this with properties of the ligands themselves, like isolated, like steric bulk or solubility, properties like this. But we also tried models in which we are mapping to properties of complexes, for example, the corresponding homoleptic complexes. So once you have optimized this, then you can do conditional generation. So now the generation of the ligands is conditioned to some target properties that you want to have. Like in this example here, we can prompt the model with this amine ligand and then ask the model to generate, to optimize a ligand that in this iridium square planar complex would maximize the charge of the metal center and the HOMO-LUMO gap. And one sort of interesting thing you can do with these models is you can actually follow the optimization because this is a gradient descent algorithm. So you can go step by step in latent space, and using the decoder you can decode what's going on in a way. So you see how this amine here is replaced by cyanide and how it installs these groups here, the CA3 substituent, etc. Okay, then to finish my presentation, more recently we've been also been interested in doing these inverse design tasks. Of course, all of this is inverse design, so that instead of defining features and then predicting properties, you actually define properties that you want to have, and then from these you get features that describe actual molecules that meet these properties that you want to have. And we are interested in this approach of combining genetic algorithms with machine learning methods. So something you can do, sort of obviously, is for example to use machine learning to optimize a surrogate function that is computing your fitness so that it does this like accurately and very fast. But there are many other things you can do. For example, have a neural network classifier to decide whether an individual of your offspring is killed or survives and is considered as a pattern for the next population. And all of this is about putting machine learning within the genetic algorithm. But you can also do this the other way around, right? So, and for example, do genetics in latent space so that you run your genetic algorithm in latent space, and then when you get your final elite population, then you decode it back to whatever molecules are represented are there. So we published a perspective about this recently, and something that we're doing now, for example, this is ongoing work now in my group, is to use this variational autoencoders and generic algorithms in a sequential manner so that one fits the other. And of course you can do this in two different orders, but so in the example here, we trained this JTVI model with this TMQMGL ligand library that has ligands from the Cambridge Structural Database to generate ligands. And then we use these ligands to fit this PL-MOGA, this multi-objective optimization genetic algorithm. And now using ligands that are not from the CSD, but made by the variational autoencoder. And you can also, if you want, you can mix both. And of course, for example, if you want to use a JTVI for multi-objective optimization, good luck. This is very difficult. But then the genetic algorithm, that's quite simple, at least with the code we have now. One example application of this is optimization of ruthenium-2 chromophores in a space that contains millions of candidates. So what we did here is we are using ligands that are made by the JTVI, by the variational autoencoder. And so we defined a set of genetic operations that operate on these octahedral complexes so that you have mutation by replacement, flip and swap. You also have crossover operations. And then we're trying a three-objective optimization here. So the three targets that we are optimizing, that we are maximizing, are both the intensity and the broadness of light absorption in the visible range and water solubility. And this is very preliminary, but we have an algorithm, an implementation that already works quite well. And the next step we really want to do now is to realize this experimentally, to get someone to do it in the lab, which is a bit difficult. People seem a bit skeptical about us taking control, I guess. So that's my last scientific slide. Then on behalf of the Scientific Committee of WATOC, I also want to make this ad commercial. Please join us in Oslo. We are organizing WATOC in June. And with that, I finish. Yeah, thanks for your kind attention.
Thank you very much. This was utterly fascinating. Do we have any questions?
Yeah, great talk. So I was just curious about this 1.5 million compound database. So the plot in 2 dimensions of the gap and the polarizability look curiously circular. So is this the central limit theorem, or so how Gaussian is this distribution? It's kind of surprising that these 2 properties that you would think are sort of different come out to be so evenly distributed.
Good question. I don't really know. We have not analyzed this at this level. But the data there is XTB, so perhaps it's something to do with XTB. Though we did some DFT verification, but more at the algorithm level at the multi-objective, but we did not compute these 1.37 million data points with the DFT method. Could be something from XTB. I don't really know. I didn't thought about it from this perspective, but yep. It's fun.
From a very broad perspective, chemistry obviously is about structures, where the atoms are, but then there's the electronic structure, where the electrons are, and in your second example, you showed how homolumo gap and polarizability are important aspects in quantifying the ultimate goal that you want to quantify. So, broadly speaking, I understand. My question is, obviously there's many more electrons, so does it then those in the HOMO or in the LUMO, does it make sense to dissect that even more into different symmetries of orbital interactions and all these things? Or does it become unsolvable, in quotation marks?
Not sure what the question is, but
I mean, the HOMO-LUMO gap is a result of all electrons interacting.
Yeah.
So
well, yeah.
does it make sense to look deeper
Yeah.
into more orbitals,
Yes,
basically.
yeah, and we're thinking about this, like for example, the orbital density around the HOMO-LUMO gap, division, things like this. Of course, like one of the problems, I think these are sort of fun toy systems to do benchmarking, but of course reality or real applications are way more complicated than this. And one of the things we're struggling with, for example, if you focus in these quantum properties like HOMO-LUMO energies or HOMO-LUMO gap or charge at the metal center, it's very difficult to, what we would like to do ideally is to then correlate this to some properties that are relevant in catalysis, for example. But these correlations are not really there, or are way more complicated. You have to take into account way more variables or targets. So we're working on this, we're exploring this, but in the end, we normally end up using energies, some sort of energy, like some thermochemistry or some energy barrier or something that correlates with the energy barrier.
I understand it, but I find it surprising because I see, not many, but I see papers of synthesis groups who in the end up with a good catalyst, but the beginning of the paper is, we thought that pipe back donation may be stronger if we do this, we tried, and it was, and here's our catalyst. So this is a way of dissecting, so there must be relations and correlations.
Yeah. But these are complex.
Yes.
Yeah, thanks a lot for the talk. Just two questions related to problem we face ourselves, and I want to ask you how you deal with it. I read your paper on the transition metal database extracted from Cambridge, but I don't remember the answer to this question, so I'm asking you. How do you extract the charges in the spin?
You mean the overall charges? The overall charges are available, are part of the data, but the problem is, so you have this property charge. Then the problem is when you have fragments, right? When you have solvents or counter-ions. Well, basically what we do there is we extract the heaviest fragments, because at least with the API that we used at the time, that was the only option. Of course, that's not very good, because you may end up in a situation where that heaviest fragment doesn't have the metal. It normally has the metal, so then we need to do an extra check on that. And then you can recover the charge of the fragment. So that fragment also has that charge defined. Now, the problem with that, there are also problems, is that that charge is not always correct. Then that's not a big problem, because then we still look or check for spin charge consistency. That means that if the error is by 1 unit, you detect that. Then there are some errors. The Cambridge structural database, I guess you probably know this, it's full of errors.
Yeah.
Still, perhaps it's only, 1% or 5% of that. But of course, each object in that database is a complicated object with lots of data associated with. And it turns out that some of this data is wrong for some reason I don't really know. There's human curation, I know. There's a lot of chem informatics also. I guess there's also sort of a history about these errors, because Cambridge structural database has been around for a long time. But then, of course, if that error is by 2 units, then still it passes, right? Because you will have a spin charge consistency. That means that there are some errors in our database, but I think they're below like 1% or, yeah.
Okay.
Yes.